this is what is the root of my search tree or a backtracking tree, whatever you call it. So that's what becomes the root of my backtracking tree. Now what I do is I need to select a variable first heuristically, and the heuristic that I'll apply is called as the minimum remaining values, which means select the variable that has the least values remaining, least values possible, least values which I can assign. It's also called as the most constrained variable or a fail first heuristic. So funny names. And let me just use it as of now, and later on I'll of course tell you the motivation behind it. So this has 3 values remaining, B has 3 values remaining, C has 3, all of them have 3. Oh god, it's a tie break. So let me just select A and assign a value to it. Red is my favorite color. Okay, we haven't looked into value ordering. And the graph that you see around over here is what is the node which will get around over here. Now, the moment you assign red over here, B cannot be red, C cannot be red, D cannot be red. So 3 values are gone. So next, which variable do I select? I cannot draw everything around over here, but I think I can just say A is equal to red was the assignment around over here. So, and this complete graph is actually inside this node. So now this has 2 values, this has 2 values remaining, this has 2 values remaining, this has 3 values remaining, this has 3 values remaining. So I again have a tie break between B, C and D, which have 2 values each. Let me take anyone. Oh my god, let me take alphabetically here. It cannot be R, so let's take a G over here. That's a G. And by the way, the moment I color this thing, then it's virtually saying that all this is gone. This node also does not remain. All the vertex is removed, the edges are removed. It's all a part of the constraint graph. It already has a value. And this way of reducing R from these nodes is what I call as a forward checking. So I checked forward and I removed illegal values so that they cannot be assigned at the first place. So at the second node, of course, what did I do was I said B is equal to G, which of course means that virtually everything is gone. It has a value now, which means that C does not get affected by B, but D does get affected by B. This is G, so it cannot take a G. And because it cannot take in a G, I will delete it from the domain. E cannot take a G. I'll delete it from the domain. So now let's look at how's the graph doing. C has 2 remaining values, D has just 1 remaining value, E has 2 remaining values, F has 3 remaining values. There's no tie break. It's clearly D which has just 1 remaining values. So because D has just 1 remaining values, I will take a D, which means I'll do this assignment. So D is equal to B. I'll also show it around over here, although usually I don't do it. D is equal to B. And all the previous ones are of course being carried forward in the branch. So now this is also virtually removed from the constraint graph. It already has a value and therefore now it affects C. C cannot take in a B. And it affects E. E cannot take in a B. So now my possibilities are C which can take just 1 value, E which can take just 1 value, and F which can take in 3 values. So there's again a tie between C and E. So now I'll not continue on the search tree. It's backtracking, you know. So let me assign C is equal to G over here, which means that this is gone. Luckily, it doesn't affect. This is all the outside the constraint graph, and this is all the outside the constraint graph. No change. Next is E, which has one value, and F, which has three values. So minimum remaining values, E with one remaining value is the one. So I select this one, E is equal to R. Of course, this is gone. It doesn't affect anything because all these nodes have already gotten values. They're outside the constraint graph. So I just have F. So I just assign it any value. F is equal to R. Now, luckily in this case, I did not have to backtrack. It's a simple problem. And I got the solution straight away in a row. Otherwise, you would have seen that I would have needed to backtrack. So the complete graph that you see around over here, it's actually represented in the nodes with all those assignments and with all those domains. And it's not that there's a central global graph like this. I knew I did not have to backtrack, and therefore I did that. Now the curious question, and I don't ever honestly answer that, why minimum remaining values? Why not maximum remaining values? The easy way to look at it is that the branching factor at any level, at any node, is equal to minimum remaining values heuristic, or the MRV. So if at all we would have expanded everything, the root would have got in 3 because the minimum remaining values was 3. This would have got 2 because when we expanded this, it had 2 remaining values, and similarly for the rest. And therefore, by saying minimum remaining values, I reduce the branching factor. Now, ideally it would appear that, can you solve problems just like that? No. If you are reducing branching factor up top, you are increasing the branching factor below. The branching factors cannot be dropped off like that. However, in this specific case, what happens is that as I go deeper, the constraints are activated, which means that MRV, or branching factor, is reduced. So take small branching factor up top. Later the constraints will take care about reducing consistently the branching factor. So that's what you see. Constraints are regularly pruning. We're not discussing pruning around over here. Constraints are pruning. They are cutting off branches. So something which, if it initially has a very high branching factor, by the time you go down choosing lower branching factor, constraints would have activated and would have already cut that. So effectively, I'm trying to minimize my number of constraints or my branching factor. So it's an intuitive way to understand why minimum remaining values, why not maximum remaining values, largest branching factor. And that's a complete heuristic in itself. Now, it turns out that we had a lot of tie breaks. In fact, we started off with a tie break. And because we started off with a tie break, can we apply another heuristic, maybe not as good as the minimum remaining values, maybe a slightly cheaper heuristic, maybe not so dominant heuristic? Can we apply another heuristic to act as a tiebreaker? And the solution is, of course, yes. So the second heuristic that we will be studying is called as the degree heuristic. So the first heuristic is minimum remaining values, and the second heuristic is what is a degree heuristic. Now what the degree heuristic says, of course, it's a heuristic on variables. We're still studying variables. And the degree heuristic says you need to select in variables which in the constraint graph have the least number of active edges. which have the largest number of active edges, or which put more constraint on the other graph, which put more edges on the other graph. And remember, it's a tie-breaking heuristic, so degree heuristic will never be used in itself. It will only be used when you need it as a tiebreaker because it's a weaker heuristic. So let's take in exactly the same graph which was around over here, and let's solve it by using a combination of degree heuristic and the minimum remaining values. So it's A, B, C, D, E, and F. And that's how my constraints are. I'll just verify that I've got in. Why should I get exactly the same? Okay, and I'll of course write down again the domain values here: RGB, 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 and RG and B. And of course, I'll not show the backtracking as a tree around over here. I'll not show the search tree. You know it by now. Now what happens is minimum remaining values 3, 3, 3, 3, 3, 3. So here's a tiebreaker. All of them have 3 values. And because all of them have 3 values, so I need to invoke the tie-breaking condition. So I count the number of edges that every variable has. And that is what I will be writing down over here as temporary brackets. So this has 1, 2, 3 active edges. This has 2 active edges. This has 1, 2, 3, 4. Oh my god, this has 4 active edges. This has 2 active edge. And this has 1, 2, 3 active edges. And this has 0 active edge, no edge. So the numbers in brackets are the number of active edges for A, 1, 2, 3, for C, 2, for B, 1, 2, 3, for D, 1, 2, 3, 4, for E, 2, and for F, 0. So now what I do is I select the one which has maximum degree. So you already know what's the degree of a graph. So the one with the maximum degree out of 3, 3, 2, 4, 2, 0, the maximum is with this, and therefore I select a D and I assign it any value, let's say R. So virtually this is outside the graph now, and I can remove these edges as well by reflecting this assignment by forward checking. So I check one step forward and I reduce illegal values from the domain. So D and C have a constraint. D is R, so C cannot be R. D and A have constraint. D is R, so A cannot be R. D and B have constraint. D is R, so B cannot be R. This cannot be R. F shares no constraints. And of course, once I have done that, that is what is my first step. Now I'll do in my second step, which is to calculate the minimum remaining values. For A it's 2, for C it's 2, tie break. For B it's 2, tie break. For E it's 2, tie break. I'm getting lots of tie break, good example. So this has 2 active edge, 1, 2. This has 1 active edge. B has 2 active edge. E has 1 active edge. F has 0 active edge. So when you deleted an edge, you could have just subtracted 1. You'll see the new numbers which are previous minus 1. Now that's a weird situation. I need to take the maximum of 2, 2. Okay, I've not compared this because F did not participate in the tiebreaker. Only A, B, C, E participated in the tiebreaker. My bad. F did not participate in the tiebreaker. Only A, B, C, E participated in the tiebreaker. So now it's 2, 2, 1, 1. I again have a tiebreak. Now, this time I really have no options. You can see it's because of the symmetry. So I make in the assignment A is equal to G. So this is gone. In fact, this is gone, this is gone, this is gone. And I'll reflect the changes by saying that A is G, so C cannot be G. And A is G, so B cannot be G. And remember, it's happening as I go down the backtracking tree. I cannot draw the same big figure every time. Okay, so now let's again calculate the minimum remaining values and see what is it going. So here C has one option left, B has one option left, again a tie break, E has two options left, and F has three options left. So there's a tiebreaker between B and C. C has 0 active edges, B has 1 active edge. E is not participating in the tiebreaker. F is also not participating in the tiebreaker. So I'll select a 1 over a 0, which means I'll assign B is equal to B. And this is virtually out, which means this is out, and I will reflect the changes on this, which is E cannot be B. So let's do it again. Minimum remaining values, one option B, one option G, three options. So again there's a tie break. Unfortunately here 0 active connection, 0 active connection. So I will have to choose anyone randomly. Again it's a symmetry. So I say C is equal to B and this is gone. It doesn't anyways affect anything. And then I say E is equal to G and then this is also gone. It anyways doesn't affect anything. And finally I have F. There's only one option, three remaining values. Tie break with nothing, so F. So I say F is equal to R. Again, I did not need to tie break. So my solution is A is equal to G, B is equal to B, C equals to B, D equals to R, E is equal to G, and F is equal to R. That is my combination of minimum remaining value and degree heuristic. Now, why does degree heuristic work? And again, I leave it intuitively. So somehow I need to reduce the branching factor. And the branching factor is just the minimum remaining values. So what happens over here what happened is that because you took D initially, it had constraints with 4 variables. It removed 4 values from the domains. Which means it put the maximum constraints, which means that it cut the maximum future branches. And believe me, the next heuristic, I'll say exactly the opposite. So be very careful with what I say. So the degree heuristic removes the maximum number of constraints from the future nodes. It reduces the branching factor of the future nodes. And therefore, it relieves maximum constraints instantaneously up top. And as I said, if you have to reduce the branching factor, the more up top you do, the better it is, because lower down it will anyways happen by the application of those constraints. Degree heuristic does exactly that. It tries to remove maximum number of values or to reduce the branching factor at the right at the top. Now, I'll have one last heuristic, and my one last heuristic will be on values. So, values are independent of variables. So, you select variable and then you select value. So, it's not that it's a tie break. It's deciding in which order do I try the assignment of the values, and guess what? I will be doing exactly opposite of what I had been doing so far, And instead of maximizing, I will minimize least constraining value. So I've gone through the entire thing twice. I'll not do it the third time. Let me leave it logically alone. So what you do is you select a value for the chosen variable. Using heuristic 1 and heuristic 2, you select a variable. Now you need to assign a value to the variable. So you assign the value to the variable which is least constraining, which rules out the least values from the other nodes, which means that you try to reduce the number of constraints, which means that you try to leave nodes with the maximum values possible. So let's take a quick example. First, I'll try to say that I'm doing it on the same graph. So in the same graph, step number 1 is that you select a variable. Variable is independent of value and you always select the variable first. And why did I get the variable D? I've already spoken about it. So let it be unquestioned, and these are the values. So by what you know, D is the variable. Now I need to select in the order in which values need to be applied. And the order in which value needs to be applied is what will make me think that, okay, which value is the least constraining. So I'll do it 3 times, 1 for R, 1 for G, 1 for B, and then make my observation. So first let me do it for R. If D is equal to R as case 1, then I will cut 1, 2, 3, 4. So let me write it down. If D is equal to R, 4 values are deleted. If D is equal to G instead, so let me say what would have happened if it would have been G. So instead, if D would have been G, the same 4 values would have been deleted. And similarly, if D is equal to B, the same 4 values are deleted. I choose the one which is least deleting the values, which is leaving other variables with maximum values. Unfortunately, it's a tie over here. And because it's a tie over here, it is a bad example. So let me very quickly make in a small graph in order to illustrate that up. And don't tell me how did this graph come, except for assume it came from something. And let us say for some reason, B was the one which was selected. The values around over here were G. This had a possible domain as a G and a B. And this has again a R and a G. Now, if B is equal to G, then it cuts 1, 2 values. I delete 2 values. However, if B is equal to B, I do not delete any values. 0 deleted values. Contrary to belief, this is more preferable. Lesser values deleted or leaving variables with more values as option. And let me draw the 2 cases up. That's why I took a smaller graph. So in one, you will have R and R. This, of course, in both cases has been assigned a permanent value, which is a G. And in the other cases, it is a G and a G. And this, in this case, of course, is G. So this has more remaining values. G is, my bad, B. B is least constraining. B puts lesser constraints. It deletes lesser values. It leaves A and C with more values. So this one is better. Now, why did I completely change my language? Why, in case of variables, I maximize constraint. I say prune more. I say let the remaining values be less. I say all those things. While with values, I suddenly say the opposite. Least constraining, more values options. And I leave it out for you. It's just something that you need to think in your head. Somebody answering the question will not help you. I'll just give you a few directions of thought, and then thinking of it is a homework. So why are variables different from values? The first difference is all variables are eventually selected. Irrespective of everything, some variables are selected first, some are selected later, but in the complete solution, all variables are eventually selected. However, not all values are tried. I only try B as a value when R fails. I only try R when G fails. So only when backtracking happens are all values selected, and therefore my rule says if it's variable, I know that if I miss this earlier, I'll have to do it later. If I miss this, I'll still have to do it. But in values, I'm like, okay, let me choose a value such that I don't have to backtrack. So with variables, I try to maximize the constraints, while with value, I say, choose a value such that the chances of backtracking are minimum, chances of finding a solution without backtracking are maximum, chances of finding a solution in the same branch are maximum. All variables have a lot of value options so that I don't have to backtrack. So the difference comes that all variables are eventually succeeded. However, not all values are tried, leading to, for variables, I maximize constraints for the reason said. However, for values, I maximize instead chances of getting a solution without backtracking. So if it's values, I'm like that, dude, select a value such that I don't have to backtrack, because you know how expensive backtracking is. I hate it. But with variables, I'm like, even if I hate this thing, I'll have to later take it. So there's a difference between compulsory question. Yes, in an examination, you could say question number 5 is difficult. However, you don't have an option. You either try it first or you try it later, but you have to try it in the examination paper, and therefore you make in strategies for yourself. So try the easier ones first, get the momentum. You still have to try the hard one. There's no choice, but you get a lot of confidence. However, when it comes to do any one of 5, then you're like, okay, let's choose the easiest one, and I don't have to do all of them. So let's choose the one in which I make least mistake. It's the same thing between selecting variables and values. In one, all of them need to be tried. You don't have an option. In the other one, not all of them need to be tried, and therefore you try to get a maximum success as quickly as possible.